Okay.
Okay. Welcome back, everybody. So this is the third lecture of the day, and it's the second lecture by Martina on symmetries. So please, Martina, start the lecture.
Okay, thanks. So welcome back and welcome to the lecture. So let me maybe just recall what we did yesterday. So yesterday we started by introducing some partial complexes, and the way you should think about it is either as a, or at least for those lectures, just think about it as a boundary complex of a simple polytope, or think of it as a triangulation of a sphere or triangulation of a manifold or something like this. So just keep this picture in mind. And then we started to introduce Macaulay complexes, which had the nice property that if we look at the H vector, which is just given by a linear transformation of the F vector, and the F vector just counted the faces, the number of faces of our simplicial complex. So if you look at the H vector for a Macaulay complex, this vector is always non-negative. This was one of the nice features which we had yesterday. And then in the last part, I started to introduce symmetries, and this is where I want to go on now. So let's just recall what we mean by a symmetry. So let's just say that we have a simplicial complex delta. Yeah, I guess you should see this now. Yeah, that we have a simplicial complex delta, and that then we say that we have a group G acting on it whenever we have a group homomorphism from G to the automorphism group of the simplicial complex. So what this just says is that if I give you a group element, then you assign to this group element some kind of automorphism on your simplicial complex. And it should be in such a way that it's a group homomorphism. So it's not like completely random, but there's some, it should just obey the rules of a group homomorphism. And then we were only interested in those which are fixed point free, which just meant that if you take any non-trivial phase, so except for the empty set, and if you take any non-trivial group element and apply this group element to this phase or the corresponding automorphism to this phase, then it shouldn't be fixed. So you should get another phase. And this is what we meant by fixed point free. And then we had like those special things which were centrally symmetric. So we said, okay, a simplicial complex delta is centrally symmetric whenever I have a group with two elements, so we see two acting on it. And this you can trace in the following way. You can just say, okay, there is a free involution on the vertex set. So here V is the vertex set of delta, and the involution I call alpha, which also induces a free involution on delta itself, also on the set of faces. So what does this mean? First of all, being a free involution on the vertex set just meant, okay, no vertex is fixed. And but if I apply this involution twice, I get the vertex back, so I get the identity. And if I do the same for any phase of the simplicial complex, then I should have the same behavior. So the image of a phase is an image, but it's not the phase itself, except for the empty set again. And if I apply this alpha twice, I get the phase. So I will usually write this alpha whenever I speak about centrally symmetric stuff as minus x, so minus the identity. I mean, we don't have necessarily some kind of geometric realization on our simplicial complex, but just this is the way how you should think about it if you have a polytope. Because there, this involution is really just mapping x to minus x. So I will use the same notation also for more general simplicial complexes. Okay, and then as a special case, we had simplicial polytopes, which were centrally symmetric, or just CS. And therefore, the only condition is just to say, okay, if you look at minus p, you just get p itself. So it doesn't change. This is everything. And then more generally, we had linear p symmetries. So now we have a group of possibly bigger size acting on the polytope. And what is a linear p symmetry? It is just a fixed point free invertible linear transformation. So fixed point free means it's fixed point free except of fixing the origin, because it has to be fixed. And it should have the property that alpha of p is a polytope itself, and it's of order p, and order p meaning just as an element of the symmetric group, but it also means that if you apply it p times, you get the identity. So this is what we had yesterday. And let me just start with some consequences. So if we have Simplicial polytope, that is CS. So there are several things which you can deduce from it. So like the easiest observation is that if P is full dimensional, then the origin has to lie in the interior. And the interior I will just write with int of P. So if P is not full dimensional, then the origin lies in the relative interior. But yeah, that's one thing. The other thing is that if X is in P, then also minus X has to lie in P. And this is an equivalence. So if X lies inside, that's even only if also minus X lies inside P. And the third thing I would like to mention is that there is no edge of the form X minus X. Well, that's just an easy observation because X, if you look at the complex hull of X and minus X, it contains the origin, but the origin lies in the interior, so it can't be an edge just because of this. Okay. So let me start by introducing a specific class of symmetric polytopes. So here, I don't want to do it in full generality. I only want to do it for the CS case. So I want to introduce CS, symmetrically stacked polytopes. Okay, so what do I mean by this? So you start with a cross polytope. So start with Cn. Start with Cn star, and by Cn star, I just denote the boundary complex of the cross polytope. So plus minus ei, I between 1 and. So that's just a cross polytope. So start with this polytope, and then just take a facet. So take a maximal dimensional face. Okay, let F be a facet. And then take a vertex and place the vertex a little bit above this facet. But don't place it too far away. So what I mean by this, I guess I just draw a picture. So you start with the cross polytope, which somehow looks like this. Okay. And then you pick any facet. So for example, you could take this facet here. So this might be F. And then you take a vertex, let's call it a new vertex, let's call it V, which you put somehow above. And then you take a pyramid over this facet. And you remove F, but you add those new facets which we obtain from the pyramid. And now do the same for minus V. So add minus V, which now lies somewhere here. And also takes a pyramid over the corresponding facet, which is minus F. So this facet here, this is minus F. So what you get is again a polytope which is centrally symmetric. And you can do this procedure over and over again, which gives you a whole class of simplicial polytopes. So in any dimension, you get for any possible number of vertices, so it should be 2n, and n is larger, at least d. But for any such number, you will be able to construct such polytopes. Okay. So take a shallow pyramid over F. With vertex V. And do the same for minus F and minus V. And then just repeat this procedure. So this works for CS polytopes. So in general, if you have any p-symmetry, what you would do on this, I will just describe in words. So I have it in the notes, but it's just a little bit more complicated. So instead of starting with a cross polytope, you just start with a simplex. So start with a simplex with rational vertices. And then, and which kind of vertices do you take? You choose p, you choose p minus 1 vertices just as a basis of q to the p. And then you add an additional vertex, which is just minus the sum of all the other vertices. And then what you do is, okay, you take those boundaries of the simplex, you put them in some r to the p, and then you just do this with several copies, and you take the convex hull. So for the cross polytope, what you do, you just take the boundary of the one simplex, because the cross polytope is just a join of boundaries of one simplices. And now instead of taking a one simplex, you take a higher dimensional simplex, where the dimension is just p minus 1. Okay, now you have at least, like, you have the analogon of the cross polytope just for a set p action. And then you do again some kind of symmetric stacking by just taking any face, any facets, place a vertex, take a pyramid, and then just do it with all the other faces you have to do it. So you just look at the orbit of this new vertex under your action. And the same for the facet. So this also gives you new polytopes, which are now p-symmetric. So it's just the analogous construction. So are there any questions so far?
I have a question.
Sure.
When you added this new point B, and you're adding the edges as well, but do you add the flat parts in between?
Do I add what?
If you see your drawing, you have a point B, and it's connected to two other points. But do you take the flat part as well?
Yes, because I have a two-dimensional polytope, and I want to convert it in a new two-dimensional polytope. Yeah. So if I only add the edges, it's not two-dimensional. It's not a polytope anymore.
Yeah.
So I remove F and I add those new facets. Okay, maybe I should write down that I actually also remove F. Okay, remove F and minus F. Okay, and I can also draw it down here. Somehow like this, I guess. Okay, so this is one construction, and just try to keep this construction in mind. So now I'm able to formulate the first bounds for polytopes and Macaulay complexes with p-symmetry. And I have prepared the slide because I didn't want to write it down. Yeah, because I mean, you see that the statement is quite lengthy. So let's just go through the statement. So first of all, what is it? It's a lower bound for the face numbers of Macaulay complexes and simplicial polytopes which have a p-symmetry, so linear p-symmetry in the polytope case. So let's just say, okay, p is a prime, delta is a d-1 dimensional Macaulay complex, which has a free p-symmetry, so free meaning again that it's fixed point free. So we don't have fixed points with the action. And in addition, p-1 should divide d. Then I define some polynomial phi delta t, which is just given in the following way. So you take the hi's, so the h vector, and you take the h polynomial, so hi of delta t to the I, and then you take the sum. And then you subtract this weird sum, or the power of this sum 1 plus t to the p-1. Okay, so this is something you can do, let's say. So what can one show? So first of all, in general, so if delta is Macaulay, all coefficients of this polynomial are non-negative. So if I know that those coefficients here are non-negative, I automatically get that hi is greater than or equal to the corresponding coefficient on the right-hand side. So I have a lower bound, which I didn't want to write down. This is why I just wrote it in terms of polynomials. Moreover, the coefficients are symmetric. Well, this is basically just because of the Somerville, which we also had yesterday, which means hi is equal to hd minus I, at least for the polytope case, but also here it's symmetric. Okay, if in addition I do not only have a Macaulay complex, but I have a polytope. So I have a simplicial polytope which has a linear p-symmetry, so which was given by this linear transformation. And if this polytope is rational, I will just say why we need this, but just let's say it's rational, meaning that all the vertices are rational. Then this polynomial up here even has unimodal coefficients, which means that the coefficient in front of t to the 0 is smaller than or equal to the next coefficient, is smaller than or equal to the next coefficient, and so on, and then the coefficients decrease. So if you look at the coefficient sequence, they at first increase and then they decrease. This is what is meant by unimodal. So in particular, I have even stricter bound than in the Cohn-Macaulay case, which is not a surprise because any simplicial polytope is Cohn-Macaulay. So now, if I look at the CS case. So first of all, let's just see what we get in the CS case for those inequalities. So if we are in the CS case, then P equals 2. So then we have then this phi delta t in this case. So if P equals 2, let's say, phi delta t is just hi t to the I minus 1 plus t to the d. So this should be in parentheses here. So in this case, what you just get is that hi is greater than or equal to d choose I. So there you can really write down the bounds. So now, in addition, we also know that for polytopes, this whole sequence is unimodal. So I mean, it's not only that the sequence is unimodal. You also, what does this mean? It means in this case even that hi minus d choose I is greater than or equal hi minus 1 minus d choose I minus 1 for I smaller than or equal to d over 2. So up to the middle, everything is increasing and then it's decreasing. So in particular, if I equals 2, you get that h2 minus d choose 2 is greater than or equal to h1 minus d. And you have equality, and this is the last statement which is written down here, if and only if delta is obtained from the procedure I just described to you. So you can only do this symmetric stacking procedure. Whenever you are in this situation, you have equality, and those are the only cases. So are there questions so far? Okay. So in general, so if you have a general P, then this more general class of symmetrically stacked polytope also attains equality. So it's easy to write down the H vector, and this is something I will put in the exercises, but it's not known if those are the only minimizers. And this is one of the open problems. Okay, so let's see what we do next. Yeah, so what are consequences of this theorem? Let's just write down some consequences. And again, this is something I will put into the exercises. Okay, wait, where? Now I'm losing. I'm searching in my notes. Sorry. Yeah, okay. So let's say P is CS. So P CS polytope. And let's assume P has 2n vertices. So F0 equals to n. Then the second part of the statement, which was just, let's go back, which was this one, which were the bounds for the polytope case. This statement implies the following. So B implies lower bounds for the F numbers. And they have the following form. It's 2 to the I plus 1, D choose I plus 1, plus 2 times n minus d, d choose I. If I lies between 0 and d minus 2, and for the last F vector entry, you get the bound 2 to the d plus 2 times n minus d times d minus 1. And this was known formally as Barani-Lovász conjecture. But this directly follows from B. So it's basically just a computation. So I just say, okay, I already wrote down, it's an exercise. I also said that it's open to classify polytopes which attain equality for the p-symmetric case, except for p equals 2. I would like to say, okay, one word concerning the assumption that p is rational. So we don't need the polytope to be rational if we are in the centrally symmetric case, because there what you can do is the following. So if you have a polytope which is not rational, so not all of the vertices are rational, you can just perturb it a little bit, and you can perturb the antipolar point in the corresponding way. So this will work. You can't play this procedure for higher p. So there you might start by perturbing something, but then you can't or not always perturb the other vertices. You have to perturb in the same way. So there you might destroy the symmetry if you do this. It's not a problem for p equals 2. And then why do you really need this for the proof? The proof of the theorem also uses the Hart-Lefschetz theorem for toric varieties, for which we need that we have a rational polytope. So this is the reason why it's used. Okay. Yeah. I guess I won't say anything concerning the proof, but I will add a proof sketch in the notes. So if someone is interested in the proof, there will be a sketch of the proof as well. Okay. Okay. So now let's come to the next part. Let's come to, let's write it on the next slide. CS polytopes and CS spheres. So in the following, I will completely restrict to the centrally symmetric case. So, and I won't speak about the p-symmetric case. Maybe one last remark. The theorem we just had also generalizes a little bit. So it generalizes also to prime powers. And there are also cases where you don't need to assume that the dimension is divisible by p minus 1, but then it just gets more complicated to state. So I just decided to stay with this easier version. Okay. Questions so far? I guess now is a good point to ask questions. Okay.
So this lower bound theorem, is it the famous theorem from Stanley, or I'm just confusing the names?
Okay, so Stanley proved it for Simplistic Polyatoms. So that's a general lower bound theorem. It just says, okay, hi is smaller than, so the h vector is just increasing. So it's just h0 smaller than or equal to h1, smaller than or equal to h2. Up to the middle, it's increasing, then it's decreasing. Here we have a stronger statement. here the statement is hi minus 1 minus d choose I minus 1 is smaller than or equal to hi minus d choose I. And this was partly proved by Stanley. So he showed the CS case, and he also showed a version for p-symmetric stuff. Then there were generalizations by Ron Ardeen and Helena Jorge. And the equality case for the CS case is due to Isabella Novick, Steve Klee, Hailun Seng, and Eran Nebo. So Stanley was involved, but he didn't do the main work, let's say. Okay.
Thanks.
Yeah. So what would I like to do now in the rest of the lecture? So I would like to speak now about upper bounds for the phase numbers for the CS case. So far we have seen lower bounds. Now I want to shift gears a little bit and want to move to upper bounds. Okay, so first of all, what I need to do is to define what is a simplicial sphere. So let me just, maybe start with some examples first. So we have already seen examples of centrally symmetric polytopes. We have already also said yesterday that there are by far more spheres than there are polytopes, but I didn't really say, okay, what do I mean by simplicial sphere? So I should define what is a simplicial sphere. So, and there now is one question, because I don't know exactly if everybody knows what's a geometric realization. So is there anyone in the audience who does not know what is the geometric realization of a simplicial complex? Please just tell me. It's not much work to just define it very, very briefly. But if everybody knows, then I don't have to define.
I would like to see it defined. Okay.
Okay,
yeah.
so I should define it.
Yeah, please.
Okay, good, great. So let's start. Okay, geometric realizations. So let's take a simplicial complex. So delta is a simplicial complex. And then I do the following. So let's say V is a vertex set of delta. And then I define the geometric realization of a phase F just as a convex hull of the unit vectors, which corresponds to the vertices in F. So for example, if you just, let's say we take, maybe I shouldn't draw this. If you just say, okay, delta is the set of all subsets of the set 1, 2, 3. So it's just a 2 simplex. So what you would do is you would just say, okay, I have this phase 1, 2, 3, and I would take the convex hull of the 3 unit vectors E1, E2, E3, and this gives me a triangle. And I do the same for every other phase. So for example, also for the edges. So now I just say, okay, what's the geometric realization of delta? It's just the union of those geometric realizations. So for delta, this 2 simplex, the picture you get is the following. So you get, here is one unit vector, here's another one, the third one, so you get this simplex, which somehow lies in there. That's a geometric realization. Okay? I mean, you can do this with every simplicial complex, so you can embed it in some Euclidean space. That's everything I would like to do right now. Okay. And now, what is a sphere? A simplicial sphere is just a simplicial complex such that the geometric realization is homeomorphic to a sphere. This is what I would like to understand by under a simplicial sphere. So let's just say a simplicial sphere is a simplicial complex delta such that the geometric realization of delta is homeomorphic to a sphere. So what are examples? So one of the basic examples, and we have seen plenty of them already, are simplicial polytopes. Just take any simplicial polytope, that's a simplicial sphere. But as I said, if you are in dimension at least 3, so the sphere is at least 3-dimensional, there are by far more, simplicial spheres than there are boundaries of simplicial polytopes. So there's a huge difference. So now what is a CS sphere? So what is a centrally symmetric sphere? You can guess what it is, I think it's just now a simplicial sphere which is already central, which is also centrally symmetric. So that's the next definition. Let's also write it. No, let's write it on the next slide, maybe. Yeah. A CS sphere, wait. Delta is a simplicial complex that is a simplicial sphere and that is CS. And here again, CS as a simplicial complex just means you have a free convolution on the vertex set that induces a free convolution on the set of faces, so on delta itself. So are there questions so far? If not, then it's a good, then one can maybe think about, so if you have a sphere, so what's the problem, or what might be a problem that the sphere is not realizable as a simplicial polytope? Does somehow mean that there is no realization as a sphere such that everything is convex. So now if I'm in the CS case, so if I have a CS sphere, there are two possibilities that avoid that the CS sphere is a CS polytope. Namely, first of all, I can just not realize it as a polytope at all. So that's just the usual thing. Or I can realize it as a polytope, as a simplicial polytope, but I can't realize it in the CS way. So I can't realize it in the symmetric way. So this is the other thing which might go wrong. Is this clear? I hope so. So there are two things which might go wrong here. And now, let's actually let's maybe just write it down first. This is part 5, I guess, already, which is the following. So what would I like to do now? I would speak about upper bounds for CS spheres and polytopes. And the very interesting feature here is that we will see that for those upper bounds, there is a huge difference between spheres and polytopes. And in a sense, this is surprising because if you are in the classical situation, then there is no difference between spheres and polytopes if I just speak about upper bounds. But I will come to this in a minute. So let me just recall what is known classically. So that's a upper bound theorem. Q2 McMullen. So what does it state? So let delta be d-1 dimensional spheres. And there is a proof by Stanley of this theorem. well, with f0 of delta equals n. So I have n vertices. Then what is known is that hi is bounded by n minus d plus I minus 1 choose I. And this is true for Cohn-Macaulay complexes, if I want to be precise, but I only want to state it for polytopes here. So what is this binomial coefficient, or where does it come from? So therefore, let's just say, okay, we have equality. So first of all, this is true for the first half of the H vector. And equality holds for what is called d/2 neighborly polytopes. So I should explain what does d/2 neighborly mean. So it's a polytope such that if you take any subset of the vertices, which has cardinality at most, at most d/2, then every such set should be a face of your polytope. So you require to be a lot of faces present. So basically you take all faces that can possibly be in a simplicial complex with n vertices up to dimension d/2. And such a polytope is called neighborly, d/2 neighborly. So are there questions so far?
Okay, sorry, there was a little debate in chat. There was a question by Andreas, and he was asking whether a simplicial sphere is just the same as a simplicial complex, which happens to be a homology sphere.
Homology sphere is more general.
So what? Okay, then I guess I'm forgetting what a homology sphere is.
Homology sphere, you just mean that you have the same homology as a sphere. If you just look at the homology groups.
Ah, okay, no, sorry. Then I think I added a different definition. I was thinking of the definition with where every link needs to be, needs to have the homology of, yeah.
But this is, I mean, this is true. The links in a homology sphere are homology spheres.
Okay, sorry. Anyway, I think that was already answered and even in the chat. Sorry.
Okay.
I'm not sure there were
anything else.
Okay.
Okay. Okay. So one example of a simplicial polytope that is d/2 neighborly is, okay, maybe I should, I write down the definition in a moment, but just let's say, e.g., cyclic polytopes are d/2 neighborly. And I won't define what a cyclic polytope is, but just for those who know cyclic polytopes, they fall into this class. And okay, let me write down what d/2 neighborly means, or maybe more general, what is k neighborly. So simplest complex delta is k neighborly. If, okay, wait. Every set of k of its vertices is a face. So for example, if it's 2 neighborly, then all possible edges should be there. So another way to phrase this, and I will also write this down because I will use this later, is to say that the skeleton, so the k-1 skeleton, and I will explain what this is, of delta equals the k-1 skeleton of a simplex, let's say, on the same vertex set. So V is a vertex set of delta, and 2 to the V is a simplex on vertex set V. So what's the k-1 skeleton? So the k-1 skeleton is just the set of faces of delta whose dimension is at most k-1. So if you look at all faces of delta that have dimension at most k-1, you get all the faces of the corresponding simplex on this vertex set. This is another way to say what neighborly means. Okay, so now what do we want to do now? I mean, I want to come up with a upper bound theorem for CS spheres. So now what one could try to do, one could try to construct maximizers, similar as in the classical case. But it's clear that the notion of neighborly doesn't work directly. Because what would it mean if I have a CS polytope? We just said that we said at the very beginning of this lectures that there is no edge of the form x minus x. So a CS polytope can't be neighborly in the classical sense. There's just no chance to be. But we can easily modify this definition by just saying, okay, I know that those edges are forbidden, but then I take everything else which is allowed. And I define neighborly in the sense. So I will just define this, and then I think then there will be a break. Well, let's just write down what's the definition. A CS complex delta on vertex set V, and let's say V is plus minus V1 up to plus minus Vn, is CS L neighborly if every L vertices of V, every vertices of delta, let's say, or in V, no two of which are antipodal, so nothing of the form Vi minus minus Vi, two of which are antipodal, form a face. And I can also write this as just saying, okay, the L-1 skeleton of delta, so all faces of dimension at most L-1 are the same as the ones I will find in the boundary of the cross polytope. Because for the cross polytope on 2n vertices, the only faces I forbid are those which contain antipodal vertices. Everything else is there. So it's really the analog of the boundary of the simplex. And this is why I can define it this way. Okay, and I think this is a good point to stop. So, okay, so what we just said before the break was to define what are CS neighborly polytopes. And we just said, okay, when do we want to call a CS polytope, so centrally symmetric polytope, neighborly, so L neighborly, whenever there are all possible faces of dimension at most L-1 present in the simplicial complex. And what are the possible faces? Those are all the faces which are of the corresponding dimension and which lie in the cross polytope. So the cross polytope is the analog of the boundary of the simplex in this case. And now the goal is to prove an upper bound theorem. So first of all, I mean, we have defined what are CS neighborly polytopes, but the question to ask is, are there any? So let's just look at examples at first. So example. So you have already seen one polytope of this kind, namely the boundary complex of the cross polytope, so CD star. So this is Cs d over 2 neighborly. And this is easy to see because whenever you have more than d over 2 vertices, you necessarily have a pair of antipolar vertices, because we just have this was wrong. Wait. Okay, let's just with 2D vertices. Yeah, so what does this mean to be CSD over 2 neighborly? It means if you take any subset of the vertices of the cross polytope of cardinality d over 2, it should be inside the cross polytope whenever I don't contain until points. And in this situation, there's even more true. Because what is CD star? You can write this as, let's say, plus minus E1 join plus minus ED, which just means you take from every set, you take at most one vertex, and those give you all the faces. And then you are allowed, whenever from each set you are just taking one vertex, you're fine. Okay, so what are other examples? I mean, the cross polytope is not that interesting, to be honest, so there should be more. So it was shown by McMullen and Shepard in 1986 that the following polytope is also d over 2 neighborly. So they showed if you take the convex hull of plus minus E1 up to plus minus ED plus minus the sum of the unit vectors, then this polytope is CS d over 2 neighborly. And now you already have 2 vertices more. So that's already an improvement in terms of number of vertices. But still, it's, I mean, not that many. So for example, how does this polytope look like even for d equal 2? So for d equal 2, you get the following polytope. So you get the unit vectors. Here, and you get the sums. So somehow here. And then the polytope is this, the 6th one. This is also CS. It's also a CS polytope and it's neighborly in the CS sense. So, but it was open for a long time. So actually just until 1.5 years ago, more or less, if whenever I have enough vertices, so let's say I have D and I have N is the number of vertices and N is greater than or equal to D, do there exist CS simplicial polytopes of dimension D which have N vertices? This was open for a long time and it was solved by Isabella Novick and Hailun Cheng, and I will mention this. Okay, so before we can state some upper bounds, let me just start with some observations which are true for CS polytopes. And let's start not only with polytopes, let's take spheres. So let's say S1 and S2 are CS d over 2 neighborly spheres. And here I'm assuming such spheres exist. And I want the spheres to be of dimension d minus 1, by what I mean with d minus 1 sphere. So let's assume I have those spheres with the same number of vertices. So with, let's say, 2n vertices each. then both spheres already have the same F vector. So in particular, they also have the same H vector, which is just by definition. But so what this says is that if I have a sphere which is d over 2 neighbor, CS d over 2 neighborly, then the F vector is, so the number of faces is completely determined just by this property. That's what the statement is saying. So why is this the case? Well, let's just prove the statement. So what we know is that S1 and S2 are CS d over 2 neighborly. So what this means is that they both have the same d over 2 minus 1 skeleton as the corresponding gross polytope. So since S1, S2 are CS d over 2 neighborly, and this is really just a definition, we know that the skeleton, so all faces of dimension at most d over 2 minus 1 are present, so all faces which are allowed to be present, so which also lie in the cross polytope. So we have the same faces as in the corresponding cross polytope on 2 n vertices. And this is true for, I equals 1 and 2. So what does this tell us? This just says, okay, then at least I know that if I look at faces of dimension at most d over 2 minus 1, the face numbers should be the same. So I have fi minus 1 of si equals fi minus 1 of s2 for I between d over 0 and d over 2 minus 1. Wait. But it should, wait, that should be d over 2. Yeah. It should, yeah, it should be d over 2. Okay, but now what do I have? Now I already have prescribed the first half of the F vector. But I also have a simplicial polytope, a simplicial sphere, sorry, not a polytope. And for spheres, we have seen in the last lectures, and I've only mentioned it without proving it, that the H vector is symmetric. So we know that the first half of the H vector already determines the complete H vector, just by the symmetry, because we have the first entry equals the last, the second equals the second last, and so on. So, but the first half of the H vector completely determines the first half of the F vector. But then the second half of the F vector is also completely determined by the first half of the F vector, just because F and H carry the same information, and I can compute the complete, if I know, let's say, the first half of the F vector, I can compute the first half of the H vector, I can compute the complete H vector, I can complete the second part of the F vector. So now I know that I'm done, because the first half is the same and the rest is determined by the first half. Okay, so since, let's just write this down, since the Dehn-Somerville equations relations state hi of s equals h d minus I of s for a d minus 1 sphere s, the first half of the F vector of a sphere determines the whole F vector. Which now tells me that the f vector of S1 equals the f vector of S2. So we have determined the first part, but then the rest is already given by the symmetry of the H vector. So are there questions so far? Okay, so what does this also tell us? So this also tells us whenever you have a CS d over 2 neighborly sphere, you can easily compute the f vector. Because you can just compute the first half. So actually we can maybe, I can write this down up here. Can write this down here. So what we know is that Fi of S1, it's the same number of faces as we have in the corresponding cross polytope. So in the cross polytope, we have 2n vertices. And we are, from each pair of vertices, for an I face, we need to choose I plus, let's just repeat. So if I want to take if I want to choose an I face from the cross polytope, so what do? So I look at my n pairs of vertices, I choose I plus 1 pairs, and then from each pair, I decide which vertex am I gonna take. So I have I plus 1 choices and choose I plus 1 choices to choose the pairs. And then from each pair, I choose 1 vertex. So this gives me 2 to the I plus 1. So this is the number of faces for such a neighborly sphere, at least up to the middle of the F vector. And then the rest I can compute from the sum. So I really have concrete numbers here. But still, this is still assuming that those spheres exist. Yeah, so questions so far. Okay, then let me just write down an exercise. And it's really a nice exercise, which also helps you to practice some of the things we had yesterday. The exercise states the following. So let's say delta and gamma are Cohn-Macaulay complexes. And let's say delta is a subcomplex of gamma. In this case, the H vector of delta is smaller than or equal to the H vector of gamma for all entries. So whenever we have a Cohn-Macaulay complex and we have a subcomplex, the H vector can only be smaller. And just to give you a hint for the proof, you should show that you can choose a linear system of parameters for both complexes simultaneously, and then you can use the algebraic interpretation of the H vector. But this just as a very, very rough hint. Okay, so why did I write this down? Because I want to use it now in the proof of the upper bound theorem for CS spheres. So let's state the upper bound theorem for CS spheres. So it was shown by Ron Ardeen in 1990, and there also exists a proof by Stanley, but this is somehow in some unpublished notes. So what's the theorem? The theorem states among all CS d-1 dimensional spheres with 2n vertices, a CS D over 2 neighborly D minus 1 sphere with 2 n vertices maximizes the phase numbers simultaneously. So all phase numbers. So that's exactly the statement you should expect from what I stated for the general case. There, the maximizer were also the neighborly polytopes. Here we have the CS neighborly polytopes. Not polytopes, we have the CS neighborly spheres. Sorry, it's spheres right now. So let me sketch the proof. Or are there any questions so far? I guess, okay. So let's say we have some CS sphere. So let delta be a CS D minus 1 sphere. On 2 n vertices. So we need to show that we can bound the phase numbers of the sphere by the phase numbers of a CS D over 2 neighborly sphere. That's what we want to show. So first of all, what do we know? So since delta is CS, so it's centrally symmetric, it for sure is a subcomplex of the cross polytope on 2 n vertices. At least again, if I identify the antipolar vertices. Because in the cross polytope on 2 n vertices, I have all possible vertices there. And even more is true because this cross polytope here on 2 n vertices has dimension n minus 1. So the boundary complex has dimension n minus 1. But we only have something of dimension d minus 1. So just by dimensional reasons, since we know that the dimension of delta is d minus 1, delta is not only a subcomplex of the cross polytope, but even of the d minus 1 scalar. So here I'm just only taking all faces up to dimension d minus 1. So nothing very serious happened. And I call the skeleton here gamma. And okay, so now what I would like to use the exercise I wrote down. So, and here is a reason why this is just a sketch. So delta as a sphere is cone Macaulay. And this is something you just have to believe me right now. So this, I know that this is maybe not immediate from the definition of cone Macaulay complexes we had yesterday, but delta, you can show that delta is cone Macaulay, and you can show the same for the skeleton here, for this gamma. And so those in the audience who know the Reisner criterion, which gives you a characterization of cone Macaulay complexes in a topological way, you would just use this criterion to show the cone Macaulayness. But for now, it's just important, okay, those two complexes are cone Macaulay. Then the exercise we just had tells us that hi of delta is smaller than or equal to hi of gamma. Well, yeah, let's say fi of delta. Yeah. Now let's write it as h for all I. Yeah. This is what the exercise tells us. Okay. This is already quite helpful. Let's just put this into a box. Wait, yeah. Okay, now I need to bring in some CSD over 2 neighborly sphere. So let's consider such a sphere. So let S be a CS D over 2 neighborly sphere. So D minus 1 dimensional, again on 2n vertices. So F0 of S equals 2n. So from the definition of CSD over 2 neighborly, we get that the skeleton, the D over 2 minus 1 skeleton of S equals the D over 2 minus 1 skeleton, again of this cross polytope we had. This was just a definition of CS D over 2 neighborly. All possible faces up to by dimension D over 2 minus 1, which are present in the corresponding cross polytope, have to be present in the sphere. So, but this tells us that the H vector, the HI of S, equals HI of Cn star for I between 0 and D over 2. And then if you put things, and even more, because the skeleton, which I wrote down here, it's also the D over 2 minus 1 skeleton of this complex gamma we had. Because what is this gamma? I first take the D minus 1 skeleton and then I take another skeleton. So first all faces of dimension smaller than or equal to D minus 1, then all faces of dimension smaller than or equal to D over 2 minus 1. So I can just, do it right away. And so I get also the skeleton of gamma here. So, which also tells me, okay, this is HI of, and maybe I write it down directly. Then I can directly write, okay, this is HI of gamma. But HI of gamma, we have just seen, and this is this box up here, this red box, is an upper bound for HI of delta. So if we put everything together, so let's just say if I take this box here, and then this says, okay, this is greater than or equal to HI of delta. And then I at least have the inequalities for the first half of the H vector. But now I can use again the Somerville. So the Somerville now tells me that H D minus I of S is HI of S. By what we have shown, we know that this is greater than or equal to HI of delta, but this is HD minus I of delta. So here I get the inequalities for the second part of the H vector. Now I have the inequalities for the H vectors, and therefore I have the inequalities for the F vector. So that's a rough sketch of the proof. Are there questions so far? Okay. Then let me, in the last maybe 50 minutes, let me say something concerning existence of those spheres and non-existence of polytopes. So existence of CS D over 2 neighborly D minus 1 dimensional spheres. Okay. So the first result is due to Yokush, who showed existence of such spheres in the 3-dimensional case. So he showed for all n at least 4, there exists a CS 2 namely a CS 2 namely 3-dimensional sphere on 2n vertices. And this for a long time was the most general result. So besides this question was open for a long time. So if d equals 3, then d over 2 is exactly what we need here. So we have something which is 2 neighborly. Okay, that's nice, but what about higher dimensions? And this was solved completely by Isabella Novick and Hailun Cheng. They constructed several classes of those spheres just in, one paper is from just last year. So it's very, very new. And they showed, okay, for all n greater than or equal to d, there exists a CS d over 2 neighborly d minus 1 dimensional sphere with 2n vertices. And I should say, so their first construction was generalizing Yukor's constructions, but now they also have found several other constructions. And one question one could try to ask is, so if we don't restrict to CS polytopes, but we want to look at other types of symmetry, so other P symmetries, are there any constructions? So can we construct, like, I mean, one could first define what do we mean by neighborly now? And the definition, it's not that hard to come up with a definition, but then you could ask, okay, are there any such spheres? So do the constructions which can be used for the CS case somehow be generalized to more general group actions? This is one problem one could look at. So now finally, and this is the last thing I would like to do, is I would like to mention that there's a huge difference between CS spheres and CS polytopes. So let me make this a little bit more precise. So let's just say I want to say something concerning the non-existence of CS neighborly polytopes for CS. Okay, so what is known? So first of all, we already have seen at least 2 existence results. To start with, so if we have seen if we take the Gauss polytope, it's neighborly. We have also seen this result by McMullen and Shepard, which has 2 times d plus 1 vertices and is d over 2 neighborly. So this is something we have on the positive side. On the other side, so let's start with the negative side. So one can show that any CS d polytope with more than, or with at least, let's say it's at least 2 d plus 2 vertices. So here we just take 2 vertices more than in the McMullen-Shepard example. For McMullen-Shepard, we had twice d plus 1. Now we have twice d plus 2. So just 2 vertices more, just 1 pair of vertices more, which doesn't seem to be much. But one can show such a polytope is at most CS d plus 1 over 3 neighborly. So for bigger d, we are far away from having a chance of being d over 2 neighborly. So this is the first result on the negative side. And these results are true to Grünbaum for d equals 4. And for the more general situation, this is also again Shepard and McMullen. So this, which also shows, okay, their result or their polytope is somehow the best you could get. Okay, so you could ask, okay, is there anything which is a little bit more positive? And yeah, I guess my short answer is no. And I would like to end this lecture with another negative result. So again, a theorem. Because the situation is worse than you would expect, maybe. This is due to Nati Lineal and Isabella Novik from 2006. So the first statement is a CSD polytope with more than 2 to the d vertices. Cannot even be CS2 neighborly. So like I mean, you can't require it to be less than CS2 neighborly. That's like, I mean, if you want to require something, then at least it should be 2 neighborly. But even this doesn't happen. So such a polytope cannot even be CS2 neighborly. So on the positive side, because maybe one should end a lecture with something more positive and more optimistic, there's also the following result. So for any dimension greater than or equal to 4, there exists a CSD polytope with how many vertices? 2 to the d minus 1 plus 2. That is at least CS2 neighborly. So whenever we have 2 to the d vertices or more, the polytope cannot even be 2 neighborly, CS2 neighborly. If we have a little bit more than half of this bound, so 2 to the d minus 1 plus 2, there exists such a polytope. And they have more or less a concrete construction. So some of the idea is to start with a cube, which is not simplicial, and to embed the cube, then to add 2 antipolar vertices to like a little bit wiggle the vertices of the cube so that everything gets CS and everything gets simplicial. And then somehow they get a polytope in this way, which has the property to be CS2 neighborly. But this is kind of, it's, I mean, the picture you see here is completely different from the one you see for spheres. And so this also tells you that if you look at the upper bound theorem for CS spheres, it holds for CS polytopes, but the bounds are not sharp at all. So there is no, I mean, we have no idea what are the maximizers in the polytopic world. So are there tight maximizers of the F vector? I mean, somewhere there should be some polytopes which maximize the F vector, but we don't have any idea. Yeah, and I think this is a good point maybe to stop this lecture.
Okay, so let's stop the recording then.